Good afternoon, class. We are looking at section 4.2, how derivatives affect the shape of a graph. We've already looked at maximum and minimum values. We're going to look at how derivatives affect the shape of a graph. Again, many differentiation formulas we should be comfortable with so we can move on. Delta x, delta y, dy, dx, linearization. Then we got the absolute and local extrema, the definition. Critical points, we find f prime, we said equal to 0 or where it doesn't exist. So f prime is 0, f prime doesn't exist. And closed interval theorem, also known as extreme value theorem. If you happen to have a continuous function in a closed interval, we must have an absolute max as well as absolute mean, and the process is outlined here. Now here's the summary of this section, everybody. A function is increasing where f prime is positive, decreasing where f prime is negative. Looks like a line with a positive slope. It looks like a line with a negative slope. A critical point of a function is a point where f prime is either 0 or doesn't exist. A relative max or mean is a critical point at the top or bottom of an interval of a graph. The function is concave up where f double prime is positive, meaning f prime is increasing. A function is concave down where f double prime is negative, meaning f prime is decreasing. So concave up, if you recall, we said like in pre-calculus, it can hold water. Concave down, it cannot. We also have this inflection point. An inflection point is a point where concavity changes. Inflection points occur where f double prime is equal to 0 or it does not exist. So let's look at the situation. Concave up, the graph of f of x lies above all its tangent lines on the open interval. Take a look at concave up. It's above the tangent line. The same thing here. Concave down, the graph of f of x lies below all of its tangent lines on an open interval. Take a look at concave down here, below the tangent line, below the tangent line. Also, let's look at this concept. F double prime is positive, means concave up. It is when f prime is increasing. I want to make sure we understand what's happening here. So the curve here is concave up. Notice if you pick up a couple of points and draw a line segment as a tangent line, this tangent line versus this tangent line, they both have positive slopes, but this is less than this one, this slope. So f prime is getting larger and larger. If you look at this one, which is concave up, this has a negative slope. This also has a negative slope, but this one is more negative than this one. On the other hand, if you're looking at the case where it's concave down, f double prime is negative, f prime is decreasing. So for example, this one has a negative slope. This one also has a negative slope, but as you can see, this one is not as steep as this one. So this is more negative in essence. Whereas here, which is concave down, this line has a slope which is positive. So does this one, but this one has a larger slope than this one. So that's an interesting approach. A point P on a continuous curve f of x is an inflection point if f of x changes concavity here. As it changes, this is the point of inflection. So how do we graph? First and foremost, we use our knowledge of pre-calculus. And then we find relative extrema and intervals where the function increases and decreases. To do so, we find f prime, we set it equal to 0, and we do the sign graph. So number line and test values between critical numbers. We find inflection points. Now, this time we find f double prime, we set it equal to 0. We make a sign graph. We figure out where the function is concave up, concave down, point of inflection, and we put them all together, we graph. Extreme values of a function are created when the function changes from increasing to decreasing or vice versa. So as you can see here, it's increasing, decreasing here. So an extreme value happens here. As we change from increasing to decreasing, the extreme value is a local max. Decreasing, increasing, in between there is an extreme value. As we change from decreasing to increasing, this is a local mean. Decreasing, increasing, this is a local mean. Increasing, decreasing, this is a local max. So the change creates that. Take a look at this one. Increasing, decreasing. So what's in between? Local max. Decreasing, increasing. What's in between? Local mean. Increasing, decreasing. What's in between? Local max. A function is increasing where f prime is larger than 0, and it's decreasing where f prime is less than 0. And we look at the proof by the mean value theorem in calculus. I quickly explain it to you. You're not responsible for that. If f is a continuous function on a, b, which is a closed interval, and differentiable on a, b, which is an open interval, f prime of c equals f of b minus f of a over b minus a. This is the mean value theorem in calculus, which basically says if there is a situation such as this one, then the tangent line is parallel to a secant line. That means they have the same slope. So if you look at this one and do the cross product, you get to this one. Now remember the concept of increasing. A function is increasing. When we go to the right, x increases. What happens to the y? The y also increases. If so, it's an increasing function. In other words, x is getting larger, y is getting larger. So in the interval of a to b, b is on the right side, and b is larger than a. So if b is larger than a, that means b minus a is positive. If f prime of x is positive, that means f prime of c is positive. So in general, b is larger than a. If f prime is positive, that means f prime of c is also positive. So the product of two positive values is positive. Therefore, f of b minus f of a is positive. Therefore, f of b is larger than f of a. And that's the definition of increasing. When x gets larger, y gets larger, because f of b and f of a are y coordinates of a function. First derivative test. Y prime or f prime is positive, curve is rising or increasing. Y prime or f prime is negative, and the curve is falling or decreasing. That gives rise to a local extremum. And as we change from increasing to decreasing, this is a local max. On the other hand, if it's decreasing first and increasing second, again, we have a local extremum, but this time, this is a local mean. And of course, we find y prime or f prime equals 0 doesn't exist. That's the possible location of a local extrema. And how do we know that? We must use sign graph to do this. The next concept is concavity and second derivative test. So y double prime or f double prime is positive. concave up. The curve is concave up. If it's negative, the curve is concave down. And again, we find y double prime or f double prime. We say equal to 0 or it doesn't exist. That would be where the inflection point could happen. You have to check it, of course. And the process uses the sine graph. Everything is about the sine graph. So a function is concave up, f double prime is positive, f prime is increasing. A function is concave down, f double prime is negative, f prime is decreasing. Now, how does it coincide with the second derivative test? When we take the derivative, second derivative, we evaluate the function at those critical points that we have already found. If the result is negative, that means the graph is concave down. So if it's concave down, we have a local max. If it's the other way around, that means it's positive, then the graph is concave up. Concave up means we have a local minimum. So in this case, we have a local max. In this case, we have a local min. So that's the second derivative. Let's look at a few examples to make some sense out of this. Y equals x cubed minus 3x plus 4. And we are also given its factored form. It may not be given, we must come up with that. So what if we want to graph this? Let's say we are going to use just pre-calculus graph it. We should have an idea how the graph looks like because we have seen this before. Number one, we need to find the intercepts. So as you can see from this part, if x is 0, y is 4, so 0, 4 is your y-intercept. From here, negative 1, 0 is your x-intercept. From here, positive 2, 0 is your other x-intercept. So that's the first. So let's first graph those. And this is a rough sketch. So we got those pairs. Now let's discuss two things, the end behavior and then behavior near an x-intercept. As far as the end behavior is concerned, we always look at the leading term. And the formula in general is a sub n x to the power of n. So the leading term is a sub n x to the power of n. So when in this case, as you can see, n is 3 and a sub n is 1. When we have an odd exponent with a sub n being positive, the graph looks like this. So that means here's the end behavior. That means when x goes to infinity, y goes to infinity. Down here means when x goes to negative infinity, y goes to negative infinity. If so, odd in general. If n is odd, but a sub n is negative, so this is looking like y equals x cubed. This is looking like y equals minus x cubed. What if we have, again, we are looking at a sub n x to the power of n, and n is even. If a sub n is positive, it will look like y equals x squared. if a sub n is negative, looks like y equals minus x squared. So I'm giving you the synopsis of what you have learned in algebra regarding the end behavior. We also have a behavior near an x-intercept. Well, here's one x-intercept having exponent 1, so we are looking at this one. Here's another one having exponent 2. Therefore, what we are looking at, this one has multiplicity 1, this one has multiplicity 2. When the multiplicity is odd, the graph crosses the x-axis. When it's even, m is even, it does not. And because of that, right here, we normally use an arrow to indicate it can't cross. So if I'm graphing this, the graph looks something like this. It comes down, goes up, has to come back down, hit the y-intercept, the other x-intercept, and it penetrates, it crosses the x-axis. So what's happening here? At this point, it can't cross the x-axis. At this point, it can. Now, what's happening here, it may look like that. It may look like that. Or it may even look like this. So up here, we have a local max or absolute max. In this case, it's local. We don't know how the shape is. So what will help us see that is calculus. So the point being, we already have an idea how the graph should look like. Let's go over details of that. So I'm going to clean up the mess, everybody. So the first thing is find y prime. 3x squared minus 6x. We want CPs. So we're going to take the 3x out times x minus 2, set it equal to 0. X is either 0 or 2. So we want to find relative extrema. We find y prime. We set it equal to 0. We find the critical points. We must do the sign graph known as the first derivative test. X, we put those numbers 0, 2. F prime is 0 at 0, and it is also 0 at 2. So you look up TP or test points. So TPs here would be like -1, between 0 and 2 would be 1, and over here maybe 3. And the reason they are going to alternate, because if you look at this, each one, x has exponent 1, x minus 2 has exponent 1, which is an odd number. So anyways, if you plug in -1 here, makes this one -1, makes this one -3, their product is positive. So this is positive. If we plug in 1 here, makes this one positive, this one negative, the product is negative. If you plug in 3, positive, positive, so it's positive. So this is what you get. What does it mean? First and foremost, it's increasing here, it's increasing here, it's decreasing here, which means increasing from -infinity to 0, union 2 to infinity, decreasing from 0 to 2. And let's throw in the arrows, and I'll tell you why. Increasing means goes up, decreasing means goes down. So right here, is the location of a local max. At what point? At x equals 0. Over here, location of a local max. At what point? X equals 2. So how do you find the pair? Put the 0 in here, gives you 0, 4. Put the 2 and do the math, and that gives you 0. Therefore, local max equals 4. How did we get that? You have to put that back into the original function. 4 at this pair. And then the same thing for the next one. And I've already explained the increasing and decreasing part. All right. Now, I want to show you that we can do this with the second derivative test, but second derivative test does half of the job, okay? And it doesn't give you intervals of increasing, decreasing. All it says whether it's a local max or local mean. That's why I'm just showing you for this question. Please don't do that for any other questions, just waste of time. If they ask you, however, you should know what that is. So we already have the function. We already have the y prime. We already have the local, we have the critical points. Let's say we don't know which one is a local max or mean. So what is the process? The process is number one, find y double prime. So let's differentiate this. So the process says we can find relative max and mean. We're using the second derivative. So find f double prime or y double prime, which is 6x minus 6. And now what is this? And evaluate the CP. So the next step is to evaluate. So we've already found this. We plug in 0. It's either positive or negative. When we plug in 0, it's negative. Negative means what? Concave down. Concave down. Looking like this, that's a relative max or local max. I hope everybody understands what it does. It just gives you the sign and you can figure it out. If I plug in 2, 2 times 6, 12 minus 6 is positive. Positive means concave up. Concave up looks like that. And that's a relative mean. So this one is concave down. This one is concave up, the shape. So what does the second derivative do? It just gives us half of what, barely half of what the first derivative test does. Tells us which one of this is a local max, which one of is local mean. You have to evaluate it. But that's all. It doesn't give you intervals of increasing, decreasing. So I just did it for this question. You don't have to do it for any other questions. We want to find the inflection points, which means we want f double prime and want to set equal to 0. We've already found f double prime, which was 6x minus 6 from the previous page. And we set this equal to 0 and x becomes 1. Now we must do the sine graph on this. And so here's number 1. And on the left side of number 1, you pick a test point such as 0. If you plug in here, becomes negative. It really alternates because it's of degree 2, but degree 1. But if you go to the right of 1 and plug in 2, becomes positive. So you should see that if you plug in 0 here, again, let me write it as TP. TP, we are choosing 0 on the left side of 1, and let's say 2 here. So this is negative, okay. And this is positive. So what does that mean? So negative, that means it's concave down here from negative infinity to 1. Positive, that means concave up from 1 to infinity. And so the arrows might help. And what is it can tell us? That x equals 1 is the inflection point. So if x equals 1 is an inflection point, we need the pair when we want to graph it. So let's put it in here. And you can evaluate it here or here, it doesn't matter. If you plug in 1 here, it becomes 1. this becomes 1 times -3 minus 3. So 1 minus 3 plus 4 is positive 2. So the inflection point has the x coordinate 1 and the y coordinate from the original function. All right. Let's put them all together. So here's the function. Here's the derivative function because it continued. And here's the second derivative. We're going to make a summary table. We have those intercepts, -1, 0, 2, 0, 0, 4. I like to come up with this table. It helps me get more interesting information. So the x-intercept at -1, 0, the y-intercept at 0, 4, it is also a max. IP, or the inflection point, at 1, 2. X-intercept of 2, 0 also is called the minimum. You can pick some other point, some easy point. For example, if you pick 3 and plug in, it becomes 4. By the way, if you plug in 3 into this, is easier because this gives you 4. This gives you 1 squared, which is 1. Anyways, let's plug in. Here's -1, 0, the first point. Here's 0.4, the second point. And it's a good practice to do this, means it's a max, and therefore when we hit that, we can't cross. That's the meaning of max, remember that. This is the next point, or the IP, inflection point. Here's the x-intercept 2, 0. Again, that's a mean, and that arrow means it can't move. And we made up another point. And we already know the end behavior. So we start from here. We hit this point. We have to bounce it back down, and that's the graph. As you can see, here's the IP. Let me write it down. Here's the IP. You can see here is concave up, here is concave down. Clearly, you can see the function, the max, the mean, where it's concave up, where it's concave down, where it is increasing, decreasing, increasing. Everything is pretty clear. We want to sketch this, and just to give you a rough idea, you can sketch this by finding the intercept. So let's quickly do that, just using the intercept and the end behavior. F of x is x squared. First of all, I hope you see that it has 0, 0. Okay. So if I take the x squared out, I get 1/2 x squared minus 1. And this gives you 0. And this gives you 1/2 x squared equals 1, x squared equals 2x is plus minus square root of 2, and therefore we have those intercepts: 0, 0, negative square root of 2, 0, square root of 2, 0. So if we just stick with that, and what I'm going to do, it's not going to be to scale, just to give you an idea. So again, this is not to scale by any means, and this is 0, 0. Let me use a different color. This is 0, 0, and square root of 2 is about 1.41. So roughly here. This is not to scale class by any means. Now, the end behavior, I'm looking at a sub n x to the power of n, where n equals 4, which is even. And that means here's the end behavior, right? Like x squared. And a sub n equals 1/2, which is positive. That's why we have the end behavior. So I have the end behavior. What about the x-intercepts? If you look at this one, this has x squared, and therefore this one has multiplicity even, and that means it can't cross it when we graph it. So if we try to graph this, it comes down, it hits the x-intercept, it has to go down, but it has to come back up at some point. Maybe we don't know that. Then when it hits this one, can't cross, has to come back down again, and it goes back up. And by the way, if you notice that it's symmetric, so they must have, because they have the x coordinate here and here, symmetric meaning f of minus x equals f of x. So if you have half of the graph, the other half is identical to that in essence, just fold it. All right, but let's do this with details, meaning let's add calculus. So we already know roughly this is the sketch. But let's differentiate. F prime is 1/2 times 4, which makes it 2x cubed minus 2x. We are going to set this equal to 0. By the way, we can find f double prime also and all of the above, and we take it from there because we're going to need the f double prime as well. We can find it now or later, it doesn't matter. So f prime 2x cubed minus 2x equal to 0. 2x times x plus 1 times x minus 1. I can do the first step for you quickly. So this one is 2x, everybody. Times x squared minus 1. Then we find this, okay? So therefore, when f prime is 0, we have 3 answers, namely 0, -1, and 1. We put this into a sign graph. At x equals -1, f prime is 0, 0 is 0, 1 is 1. And by the way, this must be in order from smallest to largest. And you can put a test point, any number that you want. And by the way, look at the exponent for each one is 1. So as long as you have one of them, the other ones alternate. So to the left of -1, again, let me just write those numbers as test points. If I want to write TPs, here would be maybe -2, -0.5 or 1/2, 0.5 or 1/2, and let's say 2. If I plug in one of them, let's say -2. If I plug in -2 here, this becomes negative. -2 plus 1, it's also negative. -2 minus 1 is also negative. Negative times negative times negative makes it negative. The rest of them, you can try it again or alternate. So let's throw in the arrows. Let's see what it means. Decreasing, increasing, this is a local mean. Increasing, decreasing, this is a local max. Decreasing, increasing is a local mean, and it's decreasing from -infinity to -1, union 0 to 1, increasing from -1 to 0, union 1 to infinity. So local mean equals -1/2 at x equals plus minus 1. I want to make sure everybody understands how we arrive at it. Just plug in 1 or -1. They give you the same answer because both of them have exponents that are even. So if you plug in 1, you get 1/2 minus 1. 1/2 minus 1 is -1/2. If you plug in -1, you get the same thing. Okay. And of course, the easiest one would be plug in 0, you get 0. You already know that. Therefore, I'm showing you that it's -1/2. So that's how we get the local mean. Local max equals 0 at 0, 0. And the concept of increasing versus decreasing was also explained. Arrow down, decreasing, arrow up, increasing, positive, increasing, negative, decreasing. It makes it very easy. When you have the arrows, you can figure out the local extreme of where they are located at. All right, the next thing is to find the second derivative and inflection point, if there is any, and intervals of concave up as well as concave down. So let's do that. Here's f of x. Here's the intercepts from the previous page. And here's the f prime that we found. Let's differentiate it again. We want f double prime. Let's differentiate it again. So we get 6x squared minus 2. We want to set this equal to 0, so we're going to factor what we can. We factor out the 2 times 3x squared minus 1. And 3x squared minus 1, if you set it equal to 0, that means 3x squared equals 1. X squared is 1/3, and x becomes plus minus 1 over square root of 3, or plus minus the square root of 1/3, either way. Let's do the sine graph. All right, again, first, I want you to notice that this has a degree 2 and it has 2 solutions, so they will alternate, and you can pick a test point, TP, and even if you don't know what this is equal to, first of all, here in between these two, this would be 0. But if you don't know what to pick here, you can even pick, I don't know, minus 100. That's fine. Over here, pick, I don't know, positive 100. So clearly those are out. Needless to say, even minus 1 and 1 will do the job. But what matters is, how do we find this? Just go with the 0 first and plug it into f double prime in this format or in this format, whatever is easier for you. When you plug in, this becomes negative. So this is negative. The other two alternate. And again, the reason they alternate, because when you factor this, it really gives you 2 answers. Otherwise, if you have doubts, you have to really check, put negative 100 or even negative 1 will do the job, by the way. Okay, if you put negative 1, this becomes positive 6 minus 2 equals positive 4, the same thing with 1. So this is negative, the other two alternate. What do they mean? It means with the negative, it's concave down. So it's concave down from here to here, negative 1 over square root of 3 to 1 over square root of 3. It's concave up from negative infinity to minus 1 over square root of 3 union 1 over square root of 3 to infinity. Okay, so that's concave up and concave down. Because it changes, we have an inflection point at this point as well as this point, and we have to put them into the original function to find the y-coordinate. So again, concave down, where it's negative in between. Needless to say, you can put it into a calculator, and we'll do that later on for the sake of seeing the graph easier. And it's concave up here as well as here, as we can see it here. Now, the inflection points there are 2 of them. One at this point, one at this point. What is the y-coordinate? Plug in, and both of them result in the same y-coordinate. So let's plug in. 1/2 of this to the power of 4 minus this to the power of 2. I hope you realize when you raise this, let's start with this one. When you raise this one to the power of 2, you get 1/3. When you get this one to the power of 4, it's 1/3 squared, which is 1 over 9. So this is 1/2 times 1 over 9. This is minus 1/3. The product of these two is 1 over 18. And minus 1/3, since this is 1 over 18, we're going to change this to 6 over 18. So 1 minus 6 is minus 5 over 18. Therefore, IP is at x equals plus minus 1 over square root of 3. And these are the 2 locations. And for the sake of graphing, we're going to change both of them to an approximation with decimals. The first one is plus minus 0.6. The second one is minus let's say 0.3 or 0.27. Why are we doing that? So we have a rough idea how to graph this. That's the reason, everybody. So take a look at the summary. We have the x-intercepts at plus minus square root of 2, which means plus minus 1.410. See, the reason we write it here, it helps us with the location. So let's stick with that. Minus 1.410, 1.410. The maximum takes place at 0, 0. And since it's a max, we put an arrow. There should be an arrow. Let me just put an arrow for you. The IP minus 1 over square root of 3, that means minus 0.6 and minus, let's say, 0.3 is this one. And the other one is plus 0.6 minus 0.3 is this one. The minimum takes place at minus 1, negative 1/2, this one, plus 1, negative 1/2. And now remember the end behavior. We are in this area and this area. Put them all together, and the graph looks like that. I hope everybody is comfortable with that. It's very straightforward, everybody. The number of bacteria in millions present in a culture at time t in hours is given as follows. N of t equals 2t times 5 minus t squared plus 14t plus 100. Find the initial population. Simply put, find n of 0. That's all it says. So if I replace the t with 0, this becomes 0, this goes away. This becomes 0, it comes away. The only answer is 100 millions. So the first part is elementary algebra. At what time before 10 hours will the population be maximized? So what it means, first of all, let me just multiply these two, and so you see, because it makes it easier for the next step, because I need to differentiate. So this is 10t minus 2t cubed, and we are going to combine this one and this one. And we're going to write it in this format, and write before 10 hours means this. So it is half closed, half open, which means we have to go through the process, and at the same time, we have to look at the end points, and only one of them is closed. We have to look at the 0 we already have, it's 100. So we have to bear in mind that number is important. Now let's differentiate that, which gives us minus 6t squared plus 24. To factor this, we're going to take the negative 6 out. And it becomes minus 6 times t plus 2t minus 2. And when we set it equal to 0, it gives us two answers, positive and negative 2. But remember, we're talking about time. Therefore, it's from 0 to 10. So we can only have a positive value in this interval. We can practically evaluate it at that point if you want to go with the sort of closed interval theorem to see that. Okay. And compare. You can also do the first or the second derivative test. We're going to look at both just so you see how we take care of the business. So the first derivative test says, here's the line. At 2, this is 0. And to the left of 2, if you pick 1 and plug it into this or that, whatever is easier. If you plug it into this, it becomes minus 6 and positive 24. They add up to a positive 18. So it's positive. And to the right of 2, again, let me just write this. For example, TP over here, we would use 1. Over here, we can use 3, or just go, crazy, pick up 10,000, whatever. So if you plug in here, it might be easier to do it here or here. If you plug in here, 3 makes it 9 times minus 6, minus 54, and 24 makes it negative. So what does it mean? As it changes from positive to negative, it creates a local max. I want you to know that. So the maximum occurs at x equals 2. And to answer the next part, we have to put the 2 into the original function. However, I want to show you the second derivative test. The second derivative test says if I find n double prime of t and then plug in this number, I got to see whether it's concave up or down and make a decision. So here's what happens. So maximum occurs at t equals 2 according to the first derivative test. Here's the second derivative test, n double prime. Look at n prime, minus 12t. Now, this is your critical point, plug it in. Negative 24 means less than 0. It means concave down, means maximum. That's what the second derivative test says. What is that maximum? Well, this 2, we plug it into the original function in this format or in this format. It doesn't matter. It's a basic, math. And you do the math. This one is, by the way, 4. 5 minus 4 is 1. This is 28. So we have 2 times 2 times 1, which is 4, and 28 is 32, and 100 is 132. And don't forget, it's in millions. All right. Here's the function f of x. And we want to find the relative extrema and intervals where the function increases. Set f prime equal to 0. Then we go with f double prime, do a sign graph, sketch the graph. In other words, everything that we've been doing before. First, I want to quickly show you how you can do that with the knowledge of pre-calculus. Okay, so to do that, let me just write this as a y or f of x equals a cube root of x minus 2 squared plus 1. So I want to remind you how we did this algebraically before. Okay. So first and foremost, the cube root of x. I hope you remember that cube root of x, y equals cube root of x looks like that. Okay. So we are moving it to the right by 2. Looking like that. Okay, so this is number 1. This one is number 2. I'm going to call it y sub 2, which is the cube root of x minus 2. Okay. Now, the next one is to raise it to the second power. So let me just write this. The next step, I'm going to write y sub 3 is the cube root of x minus 2. I'm going to square it. When I square it, this gets a little bit larger, and this flips over, looks like that. So the bottom portion, everybody, which is below the x-axis, which is negative, now it becomes positive. Why is that? Because of the effect of squaring. If it was, let's say, cube, it would get larger on the negative side. And finally, we are adding one. So adding 1 brings it up. Let's assume this is 1. In other words, I can graph this using the pre-calculus information, And even from here, we can see there is no x-intercept, but the y-intercept is this point, and it can be found by setting x equal to 0. If you set x equal to 0, it's -2. When u squared becomes +4, cube root of +4 plus 1, which, of course, a rough estimate. You use a calculator with a bunch of decimals. So you can do that. But let's do it with more details using calculus. So let's erase the mess. And so the first thing is we want to find CPs. Therefore, we are going to differentiate this. Again, first, I want to keep having this format of cube root of x minus 2 squared plus 1. This is another format. However, for differentiation, this is better. 2/3 x minus 2 to the power of 2/3 minus 1, which makes it -1/3. The derivative of the inside is 1. So this is the f prime. And we're going to rewrite this by taking this down and making it positive 1/3 or cube root. Okay. So to find the CPs, f prime is 0. The fractional format is 0 when the top is 0. So f prime of x equals 0 doesn't give us any solution because the top is any number. Any number, doesn't have to be 2. Positive, negative fraction makes no difference. Now, f prime does not exist, you set the denominator equal to 0. And if you set the denominator equal to 0, it gives you x equals 2. So how do you find CPs? Either the top is 0, which doesn't happen, or the bottom is 0, x equals 2. So x equals 2 is a critical point. Let's do a sign graph. So at 2, by the way, if you plug in 2, I hope you realize when you plug in 2, f prime is undefined. So that's why I put DNE. To the left of 2, you can pick up a test point 1. And to the right, let's say 3. And let's see what happens. I want to make sure that you can see that. If I plug in 1 here, 1 minus 2 is -1. Cube root of any negative value is negative. So the top is positive, the bottom is negative, makes it negative. But if you plug in 3, you get 1, and cube root of 1 is 1. So that's why it's positive. So down arrow, up arrow, that means decreasing here. That means increasing here. And that means the local mean takes place at x equals 2. So again, decreasing from -infinity to 2, increasing from 2 to infinity at x equals 2. And if I plug in x equals 2 into this, or this makes no difference, makes this one 0. When x is 2, 0 plus 1. That means 2, 1. So local mean equals 1. When I plug in 2, I get 1. No local max, increasing from 2 to infinity, the positive 1, 2 to infinity, and decreasing from -infinity to 2. Second derivative, f double prime. In order to find IPs, now we're going to move to this area. And again, this is easier to use. 2/3 times -1/3. The product is -2/9. The same thing to the power of -1/3 minus 1 is -4/3. I hope everybody can see that you differentiate this, you get this one. By now, you have mastered the beauty of differentiation. And so another notation for that, you take this down, make it +4/3. F double prime is 0, never, because the top is a number. Again, it doesn't matter positive or negative. F double prime does not exist when the denominator is 0 or x equals 2. So if double prime is 0, that means the top is 0. Can't happen, none. If double prime doesn't exist or undefined, the bottom is 0. Set the bottom equal to 0 and x is 2. We can do the sign graph. We can also see this is always negative. Let me explain that to you, except At 2. At 2, this is 0. But what happens if it's other than 2? Whatever this value is, who cares? When you raise it to the power of even, number 4 is even. This becomes positive times 9 is positive. The bottom is always positive. The top is always negative. Negative over positive makes it always negative. Therefore, it's always concave down except at 2. If you do the sine graph, that shows the same thing, class. To the left of 2, pick 1, plug it in here, makes it negative over positive, negative. To the right, 3, the same thing. And that means it's concave down. But it is important to know, you can't say it's concave down from negative to positive infinity. No. It's concave down from negative infinity to 2 union 2 to infinity. That's what you have to write. I can't emphasize this enough. So we got some information. We got the local extrema. Okay. We know where the function is increasing, decreasing. We know where the function is concave up, down. Okay. We don't have an inflection point, obviously. We don't have an inflection point. So we want to find the intercepts. Let's discuss that. So again, I write f of x in both formats. Okay. And the intercepts, we are saying that when x is 0, and plug in. When x is 0, you can use this one perhaps. You get cube root of -2 to the second power, which is cube root of 4, plus 1. And then this, you have to really use a calculator to see. It's about 2.6, right? 2.587. There is no x-intercept. I want to show you quickly why this is the case. But before I do that, understand when you plug in 0, you get -2. Cube root of -2 to the second power means cube root of 4. You can put it here. It makes no difference. Why there is no x-intercept? By definition, in order for you to find x-intercept, you set y or f of x equal to 0. Y or f of x equal to 0. We're going to move this number, becomes -1. Since this is over 2 to the power of 2/3, let's raise both sides to the power of 3. The left side becomes x minus 2 squared, and the right side becomes -1 cubed, which is -1. And this is always positive. Worst case scenario 0 can never be negative, has no solutions. As you know, when you want to take a square root, the right side doesn't have a real solution. So there is no solution. And that's a proof that there is no x-intercept. So to sketch it, we're going to write the minimum to 1. And then we need to pick up extra points. So we have this one. To 1. We have this one, 0, 2.5, let's say 2.6. Remember, this is 1, 2, 3, 4, 5. So 2.6 somewhere here. So we have only 2 points. What about more points? Let's pick up easy points and calculate them. For example, if I choose number 3 here, this becomes 1. When I square it, becomes 1, and 1 is 2. So 3 is an easy number. Okay. Another example, if I put -6 with -2 becomes -8, cube root of -8, -2, square it, 4 and 1 is 5. Another one is 10, 10 minus 2, 8, cube root of that is 2, 2 squared is 4 and 1, 5. So I pick up more points, and I have this point which is not so easy, but this is easy, this is easy, this is easy. You need more points. Let's plug in. So that's the first point. 1, 2. Which is an easy point again. By the way, if you plug in 1, you get -1. Cube root is -1 squared, +1, and 1 is 2. That's another easy point. 2, 1, this is the minimum, everybody. Number 3, 2, negative 13.08, negative 6.5, 10.5, and that really should give you the graph. And remember, this is the location of a minimum. So that's a graph decreasing here, increasing here. And as you can see, concave down here as well as here. And this is it.